Hello everyone. So if you recall, in the last lecture, we calculated power for individual components or resistors, inductors, and capacitors in the case that the signal or the voltage and currents are sinusoidal in nature. And now in this lecture, we're going to generalize the case and assume that we are delivering power to a network of resistors, inductors, and capacitors. And in that case, the relationship between the voltage and current are not necessarily pure like what we saw. In the case of resistors, if you recall, there was no phase difference between the voltage and current. In the case of an inductor, the voltage was 90 degrees ahead of the current, and in the case of a capacitor, the voltage was 90 degrees behind the current. But in the general case, the phase relationship between the voltage and current is not necessarily any of those cases. It could be anything in between. And for that general case, you can actually write the equation for the instantaneous power, the power at any moment in time, like this. So the voltage is assumed to be a sinusoidal function with a maximum voltage of Vm and a phase of theta v at an angular frequency of omega. And the current is going to obviously have the same angular frequency. We discussed this, assuming that all the components inside the box are linear. The frequency, angular frequency or frequency, is not going to change. What's different between the current and voltage is only the amplitude, obviously, and the phase. So now if you multiply the two by each other and you do a little bit of mathematical manipulation, you can write the result in this form that includes three distinct components. So the first component is a constant value, and that's equal to the maximum of the voltage times the maximum of the current divided by 2 multiplied by cosine of the phase difference between the voltage and current. And you see the same term showing up here, but it's actually changing at a frequency 2 omega t, going up and down, and then a different term shows up here with it basically that is multiplied by a sine of 2 omega t. And quickly remind ourselves and do a sanity check and see what how this general case would collapse to any of those specific cases. For example, in the case where this was a resistor, theta v and theta I would be the same. So cosine of 0 would be 1. So these two terms turn into 1. And this term down here is going to actually turn into 0. Sine of 0 is 0. So this term completely goes away. You get Vm divided by 2 plus Vm divided by 2 cosine of 2 omega t. And that's exactly what we calculated for the case of a resistor. So this general equation obviously collapses back to any of those specific cases that we discussed last time. Now, if you recall, we made sense of that, for example, in the case of a resistor, by saying that this portion, the constant portion of the power delivered to a resistor, is the part that is actually, on average, turning into heat. This portion is the same average going up and down, so the maximum instantaneous power is actually twice as this much, and minimum instantaneous power is 0, and on average you get something between 0 and Vm times Im divided Vm times Ym, which is Vm Im divided by 2. So just quickly remind you, the power looked like something like this, and the average was Vm Im divided by 2, and it would go up to Vm Im and down to 0 in the case of a resistive load, and that's what you would get from taking this equation and assuming theta v minus theta I is equal to 0. So with that sanity check, now we're going to actually deal with this, kind of try to better understand this equation and start defining a few more variables that we're going to use from now on. So this part of this equation, we're going to give it a name from now on. And this is called, so this is the instantaneous power, right? So this part is called the average power. Okay, so we take the maximum of the voltage, maximum of the current, multiply by each other, divide by 2, and then multiply that by a cosine of the phase difference, and that's the average power. In the case of the resistor, that was the average power that would be consumed and turned into heat, for example. Now, this cosine of the phase difference, we're going to call that power factor. And this is actually shown by P. Now, this part of the signal is called, this part of the power is called the reactive power, and would be shown by Q. And also sometimes this sine of theta V minus theta I is called reactive factor. So PF, and this is RF. So I can rewrite this equation in the form of a P plus P cosine 2 omega t minus Q sine 2 omega t. Now, let's make sense of this. So the average power is actually the part of the power that was consumed or turned into energy transformation between electrical domain and non-electrical domain would exist that was that wasn't reciprocal. In other words, once the resistor take the electrical energy, turn it into heat, it's gone from the electrical domain. This portion of the power, on the other hand, we if we recall, for example, in the case of an inductor where theta V minus theta I was 90 degrees. In other words, the voltage in an inductor is 90 degrees ahead of the current. Then cosine of this value would be 0, so that part is gone. This term was gone, and the only remaining term would have been this third term in the instantaneous power. And in that case, sine of 90 degrees is 1, and you're going to get Vmim divided by 2 sine 2 omega t. And we know that this portion of the power is basically the portion of power that is not being consumed. In other words, it is being conserved by the inductor in the form of a magnetic field, and it would come back to the electrical domain completely, assuming the inductor is an ideal component, and it basically the energy would go back and forth between current to magnetic field and magnetic field back to the current delivered to the circuit in each half cycle of that sine 2 omega t that we saw last time. And therefore, these names kind of indicate that property of the power. The average power is the consumed portion of the power, or the portion of power that is completely transformed to a different domain. And this reactive power is the portion that is actually still kept in the electromagnetic domain, and it would come back to electrical domain periodically with sine 2 omega t. Now, in the case of an inductor, this value Q is this whole value Q is actually ended up being a positive number because this is 90 degrees. In the case of a capacitor, because the voltage at that point is 90 degrees behind the current, this would be minus 90 degrees, and sine of minus 90 is minus 1, so Q would be a negative number. So when you calculate this Q, the reactive power, if you deal with a positive number, that means that your circuit is turning portion of energy into a magnetic field and conserving it in that form. And if it's a negative number, it tells you that the energy is being transformed in an electric field and conserved in the form of a charge. So a capacitive load or an inductive load in that sense. depending on how the voltage and current are related to each other, the phase of the two. So all that said, now we can examine this on a simple example and kind of make sense of it quickly. Okay, so now let's try to calculate these values for an example. Let's imagine that Vt is equal to 100 cosine of omega t plus 15 degrees, and then It happens to be 4 times cosine of omega t minus 45 degrees. So with that, now the average power P is equal to 100 times 4 divided by 2 cosine of 60 degrees, and the reactive power would be 100 times 4 divided by 2 sine of 60 degrees. Now cosine of 60 degrees is half, sine of 60 degrees is square root of 3 over 2. Both of these values are going to end up being positive numbers. So what that means is that this load, assuming that this is the voltage and current that is measured for that load, is consuming an average power equal to, if that's half, that's actually 100 watts. And Q being positive, if you recall, is going to tell us that we're dealing with an inductive load. In other words, this same load is actually conserving this amount of power in the form of a magnetic field. So, and the unit for this one, again, it's watts, and unit for this one is volt amp reactive. So the difference between the two we're going to indicate by using a voltage, a unit of watts for the average power and unit of voltage amp reactive for the reactive power. Value being positive indicates an inductive load for the case of reactive power, and value being positive in the case of the average power indicates consumption of the power. And if this happened to be a negative power, it just tells you that this amount of real power per unit of time is basically energy being generated by that. The same meaning that we discussed before for positive and negative extend itself to the case of steady state. What's new is the portion of the power that is reactive and is not really being consumed or generated, is just being conserved. And that's the difference. Okay, so with that, we're going to stop this lecture and come back in the next lecture and start looking into whether or not we can use the concept of phasors to represent the same kind of calculations in the phasor domain, and hopefully take advantage of simplicity of using phasor the same way that the phasors helped us do circuit analysis without the need to do any differential equations. When we are only dealing with the steady state, we will see that usage of phasors would help us with the calculation of power kind of the same way. Thank you.